All right. So welcome everybody. You've chosen the path of sums of squares. Welcome. So just in case you didn't mean to, I posted on Piazza about we're going to do two parallel things today. The other one is about sort of the optimization toolbox. What's a linear program, quadratic program, and on up. So we're going to try. I felt like there were two different needs sort of in the audience, and so we decided to try splitting it up and addressing both of those needs. On this track, we'll dig a little bit further into the sums of squares side of things. There's a lot to know, and I think you can use the tools pretty effectively without knowing every detail. But I still think that there's a bunch of details that to even use the tools well, it would really help to know a little better. So it's nice actually that we have a smaller group here that you guys can just really fire questions at me. But otherwise I'll start. So roughly in lecture 7, we were talking about global analysis with Lyapunov functions. And we developed the extra tools for doing regional analysis, region of attraction analysis in lecture 8, and dug more into the sums of squares side of things. So mostly the ideas just work. It's not too much harder than the global analysis. If you can show that V dot is going downhill over some region, and if that region is an invariant set, right? So if you're saying V dot is going downhill, that's part of the condition. You also have to make sure that you'll never leave the set, right? Because if you had some random circle where V dot was going downhill, you could go downhill, but just walk away from that and V could go uphill again, right? So with those two conditions together, which we get implicitly by choosing a sub-level set of V to be our invariant set, right? Then we can talk about the regions of attraction being sub-level sets of V. So we just want our V to be positive, and then anywhere where we have V less than some scalar, if we can find some scalar rho, where V less than rho implies that V dot is less than 0, then we've proven that this V less than rho, the sub-level set of V less than rho, is an inner approximation of the region of attraction.
Can I ask something about that? Can I ask a question? It has to be, so in that order for something to be a sub-level set,
again, all of the variations of you could have strictly positive definite, strictly negative definite, you can prove asymptotic, exponential convergence. All these different details can come in and matter too. There are also lots of different ways to formulate those different optimizations. I put a few of them on the board in lecture. I actually spent some time this morning really trying to fill in the notes on this, and then so those probably weren't there when you read them the other day, but I wrote through the basic reason of attraction, and then the alternative, what makes it good and bad, and there's the equality constraint formulation, which I wrote quickly on the board in the lecture. But these are all hopefully solid in the notes now. If you catch anything, please tell me. Okay. All right. The other piece we spent some time in. I know we got ahead of it a little bit in the last mini lecture, but in the lecture 8 video, we talked about the basic sums of squares tools, right? Where you're minimizing subject to some constraint saying that a polynomial P with coefficients alpha is a sums of squares. That's the way we write it. And you're allowed to have objectives and constraints that are linear functions of those coefficients. Okay, so if there's the most important thing that maybe when I was rewatching the lecture thinking, I hope it lands, right? I really hope you understand, is that you even though you're doing something clever over polynomials, the optimization is still linear in the decision variables. Those constraints are linear in the decision variables. So the times that the thing that makes or breaks what you can do is basically if you ever get things that are nonlinear multiplied together or something with decision variables that are multiplied together, then that's no longer a convex constraint. It's the coefficients of a polynomial enter linearly, and those are the places where you can put your constraints. So we'll see the different formulations. Some of them you can't optimize both the level set and the controller at the same time, for instance, because they end up multiplying. Sometimes with some tricks, you can move things around and get things to go through, and we'll talk about a few examples. And then the equivalent of the sort of Lagrange multipliers that we have in traditional constrained optimization, we have this S procedure, which allows you to say things like, I need my polynomial to be positive, but only where this other polynomial is negative, for instance. And there's a couple of ways that we wrote that, and on the board I wrote it as when g of x is less than 0, that implies that p of x is positive. That's one way to write it. Equivalently, you could say for all x, just define that set explicitly and say that p of x is positive for all those x's. Those are our tools. That's our machinery. Do you have, do you feel reasonable about those ideas? Yeah. Then we talked about, the different sums of squares formulations for region of attraction. Again, I put some more in the notes, and the fact that most robot dynamics are polynomial. So we'll spend some time on the regions of attraction. In particular, I know I had a question about control design that I'll try to speak to today. But at this summary level, anything you guys want to bring up, dive into?
I have a question. So you mentioned that if we have decision variables.
Oh. Again, I put some more in the notes, and the fact that most robot dynamics are polynomial.
Oh, so can you hear me?
Attraction in particular, I know. See, I'm recording on YouTube at the same time today, and I think I was watching myself in the background. My bad. Okay, please ask away.
Okay. So you mentioned that when we have decision variables that are, for example, multiplied together, you can't write that as a convex optimization, but it can still be written as a nonlinear program. But so I guess can that still be useful? Of course, you wouldn't have a guarantee to find a solution, but if you find one that's feasible, I guess it could be useful.
Very useful. Super good question. So yes, we can definitely. So we're going to see some examples of that where we. One way to do that nonlinear optimization is to alternate between convex optimizations. Okay, you might say let's just do gradient descent on the objective, but which is you totally can do, but you have to think about that you do have some fundamental constraints like those semi-definite constraints. So you'd have to do something like projected gradient descent or some other way to try to keep yourself enforcing the most essential constraints while going down that objective, right? So just a naive gradient descent wouldn't take into account those constraints. Does that make sense?
Yeah, so you're talking about the semi-definite constraint on the P matrix, right?
Mm-hmm. Yeah.
Okay.
So even if you were to call a more generic constrained nonlinear optimization tool, we're going to use SNOPT a lot starting next week. Is one of them, sparse nonlinear optimization. You would have to tell SNOPT that's a sequential quadratic programming method. Somehow you have to convert that semi-definite constraint into something your nonlinear optimizer can consume, and not all of them accept that in their API by default. You would typically have to make some approximation of it. But other than that, yes, totally. So I think because of those difficulties, and because a lot of times we will often do alternations instead. So we'll take two variables that are multiplied by each other, basically fix one, solve for the other with a convex optimization, fix the other, solve for this one with a convex optimization. And that is, you should think of that as just a way to do nonlinear optimization, but leveraging the fact that each half of your problem is convex. Awesome question. I sure hope there weren't other questions that I didn't hear because of my silly audio thing.
I tried to ask one, but I kind of figured it out as you were talking.
Oh,
but it was super awkward. I just started talking and you just kept going.
Oh, rough. Okay.
Can I jump in with a question?
My bad. You sure you don't want to ask it again?
Yeah, I mean, I was just like trying to reason about what exactly it means to be a sub-level set. And a sub-level set means, sub-level set is every point in like Rn or whatever your operating space is, where some function is less than a value, right?
Correct.
So what you said with that first line there, like the v of x greater than 0, v of x less than rho thing, it's basically if you have a sub-level set for some rho, where on that sub-level set, v dot of x is less than 0, then that sub-level set is a invariant.
Correct.
Is that the statement?
That is the statement, yes. Well said. And you can appreciate by your question that it can get more complicated. If you have a function that has, where the sub-level set could have disconnected components.
Yeah,
right?
exactly.
And you can imagine treating all those, and you certainly can, right?
Yeah, I was just working on exercise 9.2, so you had me thinking about this already.
Nice. Okay, good.
Quick question about the in the notes you talk about how the cost function from LQR is a candidate Lyapunov function, which surprised me a little bit. But then I suppose it makes sense because the cost to go should be decreasing as you like approach some goal state. When is it not just usable as a Lyapunov function?
Awesome. So I think the connection between Hamilton-Jacobi and Lyapunov is super important, right? So the connection is roughly that if your cost is positive everywhere, so you only ever get worse. There's not like some magic place where you get reward, right? That's only for reinforcement learning, not for control. No, but if your cost is always positive, then the cost to go function is a valid Lyapunov function. It's a hard one to get because the Hamilton-Jacobi equation is an equality constraint equation where you have to solve some partial differential equation. And you can think of value functions, or Lyapunov functions, as being just changing that hard inequality to an hard equality into an inequality, which is a much easier. So there's many Lyapunov functions that can prove that something's stable where there's like a unique cost to go function.
Okay. Oh, yeah, that makes sense.
So the statement of using LQR is basically, the more general statement is if you can take some fixed point that's stable by a controller or is just a simple system that's already a closed loop system, if the linearization can reveal that it's stable, then linear Lyapunov function, a quadratic Lyapunov function found with the standard Lyapunov tools for linear theory can give you a good guess. And then you could say, for what region does the linear cost to go function, the quadratic Lyapunov function, also certify the nonlinear system?
Does this connection go both ways? So we can use like our cost to go we've solved for control to do like robustness analysis or like analysis with Lyapunov functions. If we have like a Lyapunov function, can it approximate a decent controller for us somehow?
Awesome. Yes. So we're going to talk a little bit about the control implications in a minute. That's a big part of what I prepared here. So, but basically, yes. There's an extra condition saying my v dot that you can say there exists a control for which v dot would be less than 0. That would be a control Lyapunov function. And then if you were to then solve for a control Lyapunov function offline or provide one, then you just have a job at runtime of finding some controller that is going downhill. But that tends to be a much easier problem. There's no long-term look ahead. You just say, find me instantaneously some vector that goes downhill.
Okay, thanks.
Oh, these are great. Yeah, good questions. It's even better when I can hear them. Okay, yeah. So maybe even before I jump into control design, do people feel like they understood the different alternative forms of the region of attraction? Is it worth stepping through those a little bit? Yes, worth, okay. Again, I did try to write them more nicely in the notes. So the first form I wrote, we said that if for all x, if I say v of x less than rho implies v dot of x less than 0. That's kind of the one that's the most natural. And if I were to use the S procedure to write this, then that says that I want to write negative v of x as sums of squares, but in order to make it only valid over this interval, I'm going to allow a Lagrange multiplier Okay, so the way you should be thinking about that is that this thing needs to be, so I need to be careful and write. Okay, so clearly if this is just negative everywhere, I could set lambda, I'm going to search over lambda here, right? So find me some lambda of x for which this is true. I'm going to search over lambda here. If v of x was just going downhill everywhere, I'd be done. I could just set lambda to 0. That would be no problem. Okay. When v of x is greater than rho, then this thing is actually positive. Make sure I'm pointing. If v of x is greater than rho, then this is positive. This is positive. So this thing, when it's outside the region, is allowed to help make this thing more positive. Okay, so it makes the problem easier. When v of x is greater than rho, it's adding positive terms, which can cancel out negative terms here, which means that even if v dot is not, I mean, this negative sign makes my English language more complicated, but if v dot was somehow going up outside the region, that's okay, because I can push it back down with this. Okay, but when v is inside the region, this lambda will try to make that term as small as possible. Okay, because this could otherwise hurt you. That's why lambda is a polynomial. It could be in the scalar case, maybe it's just think of it as alpha 1x, alpha 2x squared. Okay. But it's a fixed degree polynomial, so it really does only go up to some degree that you pick. The pain point here, one pain point here, is that we don't actually know what the degree of that polynomial needs to be, because this is trying to do a fairly complicated thing. It's trying to not add any terms when rho is hurting me, or when v minus rho is hurting me, and it's trying to add a lot of terms when it's supposed to be allowed to help me. Right, the ideal thing that this term would contribute would be if I were to just on the line here, think about just x, and think about some interval where v of x is less than rho. The ideal thing would be that this term would contribute absolutely nothing inside there, and then a lot outside there. It's basically trying to approximate something that doesn't hurt me. This is my lambda x times v of x minus rho. It's trying to contribute nothing, so it doesn't make the problem harder to satisfy here, and then contribute a lot up here. Okay. Awesome. The problem with this, as we just talked about, is that if I want to say maximize rho, I want to find the biggest sublevel set. So if I wanted to, it would be tempting, very tempting to say maximize rho. My decision variables would be now rho lambda of x, and then all those, this term above. Okay. But we can't do that out of the box because we get terms that multiply the coefficients of lambda and the coefficients of rho. Right, so this is the game we play. Can we find a way to write it differently so that it is convex? And there's at least one good way to do that I put on the board and in the lecture, but I'll make sure we don't have any questions here. And I wrote it up more carefully in the notes this morning. So the new way would be to have a different implication, saying that if when v dot of x equals 0, then that would imply that I'm outside the box. Okay, so that means v of x is greater than rho. And there's one gotcha for x equals 0. So take a minute to appreciate this. Think of the right picture for you here. I think I need 2 dimensions to make this one work. x1 and x2, okay? Let's say I've got some region of attraction that I'm trying to verify, which is my v of x less than rho. I guess that's the equal to rho level set that I've drawn. I'm trying to certify inside, I want v dot of x less than 0, right? Somewhere outside, I expect v dot of x might be positive, it might be less, okay? But let's say v dot goes up somewhere, okay? But there's some boundary where v dot x equals 0. And what I need is because this is a continuous function, v dot is a continuous function, if it's less than 0 on the inside, anywhere that it is positive must be on the outside. That is a sufficient condition. Maybe it's never, maybe it's always negative and then we're fine. We've certainly certified this. But anywhere, the implication is anywhere that v dot is 0, then v must be greater than rho. Except for the annoying case that it also, for our stability, happens to be 0 at the fixed point, at x equals 0. So we have to do a little extra trickery to get that one out. Okay, is that picture clear? So I've got some v dot is mostly negative, but it might be positive as long as it's change from negative to positive happens outside my region, then I've still certified it. The cool thing is that this gives me better equations that are jointly convex in the level set rho, because now I'm writing v of x minus rho is I want to be sums of squares. I want that to be positive, but it only needs to happen when lambda x v dot x. And then lambda x in this case is free. It doesn't have to be positive. This is the equality constrained version of the S procedure, because that's an equality instead of inequality. The idea is that when V dot is 0, then no matter what lambda is, it's not going to do anything. So this must be true. When V dot is non-zero, lambda is allowed to do anything it can in its finite degree polynomial power to try to make this positive, right? Cheat as much as you can, beg, cheat, and steal your way into achieving positivity. Okay. Then this annoying extra case to make it also true for x equals 0 without making something non-convex. The way that we're going to do that is we're going to hit this and make this go to 0 at 0. And the general form of that is actually, it could be anything to the d power. We're basically adding a special case of x equals 0. So that's a little bit harder to look at, but you can see that achieve the goal that now I am jointly convex in lambda and v. So now I really can do max over rho lambda, maximize rho, subject to this. There's another super nice thing, okay? Actually, a pretty recent paper from Shen, who was in my group and just graduated. But it turns out that when you're working with equality constraints in the S procedure, you can do some really nice things. So one of the pain points, like I said, is that we don't know what the degree of lambda is. Just to maybe excite you, I hope, but if you care about algebraic geometry at all, there's like super rich connections between, I mean, sums of squares is algebraic geometry. Its optimization meets algebraic geometry. And in fact, if you were to find a different coordinate system that lives on the algebraic variety of this constraint, via Grosvenor bases would be a classic approach to doing that, then you can actually remove this constraint. That would be quotient ring sauce. I said way too many words. I wrote them in the notes too, but all I'm trying to do is, if you know algebraic geometry and you like thinking about quotient rings, there's things to look up here. If you don't know, you haven't done algebraic geometry yet, then put it on your list. So it turns out that thinking about the class of functions that live on that live in the quotient of some equality constraint of a polynomial is way better than an inequality constraint of polynomials. It's the difference between algebraic geometry and semi-algebraic geometry. And there's really good tools that you can invoke when you're living on this equality constraint instead of an inequality constraint. So so this problem up here was living on an inequality constraint, a semi-algebraic set. It had to be verified inside the entire region. This one down here just needs to be verified on some equality. And because of that, you can do cool things. And the most recent cool things, which came from Diego Fuentes, who worked with Pablo, and then Shen brought it into our world, is this idea that you can actually completely remove this term using only sampling. You don't even have to solve for the Grosvenor basis directly. You can just sample your way out of it. As long as you sample enough, you can check some linear algebra condition and things get really slick and really fast. So that's just to say there's a lot to possibly think about here. Okay. So what happens when you're doing control design, right? So the standard, there's a couple different ideas in control design, I'll tell you, but let's just appreciate the basic fundamental problem. The best case, the simplest way to think about it is when we have x dot equals f of x, we have control affine, like we talked about even in the lecture 1, right? Whenever our actions are torques and we have multi-body systems or whatever, this is good, this is true. So we'll exploit it if we can. And let's say we want to now search for some controller that's a general polynomial function, let's say, of k. We'll call it k, right? It has some coefficients in here. Maybe we call them alpha, and we want to somehow search over alpha. But the trick is we want to search over alpha and the proof of alpha simultaneously, right? So we want to ideally search over v and alpha and k at the same time. If I stick this in, if I have some candidate function v, which is maybe some other parameters, and I start looking at v dot partial v partial x times f1 of x plus f2 of x k of x, then you can see again almost right away the coefficients of these two things we care about multiply. So that is the fundamental problem of searching, for polynomial Lyapunov functions with this. We have to somehow get around that. And one idea, like I mentioned a minute ago, which is a general approach to bilinear solving, is to do alternations. It's a way to do non-convex optimization. Via simpler convex problems. So if we took idea 1 above, I mean, the rough idea, let me even say, we're going to fix k of x, have some default initial controller, maybe it comes from LQR, find v of x. Okay, then we'll fix v of x, try to find a better k of x, and repeat. And that can work really well, actually. And so this gets us, remember the power of this is that we're proving it for all x, right? Of systems of pretty awesome, like well beyond what we can do with discretized value function, value iteration kind of approaches. And we're getting a real certificate, like the same way we did for a linear control on a linear plant, okay? It's never quite this easy because what we're looking for, if we're doing regions of attraction analysis, you might have to also include an alternation for lambda. So you ended up doing a 3-way alternation. Find my Lagrange multipliers, find my Lyapunov coefficients, find my k. That's actually the one that is probably the first actionable one given these ideas. But you can do that. And that is, when it works, it's awesome.
Can I ask a question about the alternations then?
Of course, yeah.
So one question is like, what kinds of problem? Okay, well, one practical question is like, what kinds of problems you can solve for this? Like how, if I have this like 3-tiered alternations thing that now sort of is a picture of a practical way to solve the problem, generally, how good do my initial guesses need to be for this to work? Like, is this something that I would do for long-ish horizon problems, or is it like pretty well-defined? I basically know what I'm doing, and I even like roughly know what region I'm talking about. So that's like one question. And the other question is, do people consider more like different means of thinking about these like alternations as like proposals, for instance, where I like sample a whole bunch and like see what I converge to in this like alternating procedure / use some kind of like bottom up neurally based parameterization to do any of those things.
Nice. Okay. Good. So let me try to. Please keep coming up with questions. Let me get those two out of my head. So here's an example of something that definitely works, right? So if you take the Acrobat at the top, you start with the LQR controller. You can prove a relatively small region of attraction for it, because and that is, well, let's even talk through that. So the linear controller you get from LQR at the top will give you some region of attraction that you can prove with sums of squares. If you even just want to find another linear controller that stabilizes the top, which by the metric of a bigger region of attraction that I can certify, then you can already do better. Because the linearization only looked locally, the non-linearization can actually give you a bigger region of attraction. So this is like I had a pretty good guess, I made it better. You can also open it up and say, I want to consider cubic controllers and other things. And each time you do that, you'll see you can certify bigger and bigger regions of attraction. That you stop when your solver says it takes too long or runs into numerical difficulties. But in principle, you can just keep growing that. Okay. For the horizons, so you should think about Lyapunov as this way to like completely abstract away time. So Rich Sutton, he always says, oh, control theorists, they never figured out how to abstract time. Somehow it's always time goes forward, and this is the biggest thing that control theory missed. And I'm like, Rich, dude, Lyapunov functions are like the ultimate abstraction of time, right? You can prove something about this function. It doesn't say anything about how long it takes. So arbitrary horizons are fine. Now, if you're trying to do sequential things, then you can compose Lyapunov functions, and we'll talk more about that later. But the notion of horizon in this, we're going to talk about the Lyapunov functions along trajectories, which I have a time varying, and there's ways where time can enter back in. But the first answer I want to give to that is just that Lyapunovs magically get around time. They
right.
Abstract it away.
I think I meant I meant much more like the first thing you said. I was using time in kind of a loose way, or horizon in a loose way, to just mean like my starting region, like how much can I sort of grow that?
Yeah. So I do think it's more. So the Acrobat is a good example because we've thought about it together, but it can do much more than that. Systems where the linearization didn't work in the first place, it can find controllers, and it can often find like much bigger, different, better controllers. For instance, we can find the swing up controller for the pendulum from kind of from scratch. So I don't have that one typed in yet. But I will type that in. So these, that's low dimensional. That's which we do mostly to think about it. But I guess the place we pushed this the most a few years ago was for quadrotors flying fast through and airplanes flying fast around obstacles and things like this. So that's a pretty complicated system. We got tens of state variables and very non-trivial dynamics, including like actuator delays and everything to get it really working, and obstacles that were moving at runtime. So it really does go pretty far. It doesn't solve like 1,000-dimensional, it's in the tens of dimensions, state dimensions typically, but that's a thing I have to be careful saying, because it's really the degree of the multipliers and things like this, the degrees of the polynomials that will come in and change the size of the sums of squares decomposition that you have to search for, and that's what kind of limits your optimizer's performance.
Quick question.
Yeah.
So for this alternations approach, the thing that it reminded me a lot of was EM, and I was wondering, like expectation maximization, is that like one instantiation of alternations, or is alternations a specific type of EM, or is there no connection and I'm like overreading it?
you're right on. I think of it that way too. I mean, EM, so I sometimes even use it, EM, as kind of this general alternation strategy. You know, there is a narrower definition of EM with Gaussians specifically and whatever. So in spirit, they are very similar. They are connected. If you forced me to choose like a containment, I would say that EM is an alternation algorithm.
Right. Okay.
But I think the analogy is very strong. Okay, so one approach is really to do alternations. Now that we appreciate why K and V even hit against each other, so you have to fix them, right? And again, with lambda is going to touch V, lambda times V in most of our formulations, but that can work. There are other big approaches out there, right? One of them that has gotten more popular lately, well, there's multiple ways to do convex reformulations of the problem. One of them is outer approximations, and I did write that up in the notes also this morning. So let's decide if we want to go into it or not. But let me just roughly one of the reasons that doing what you'd like to say is like for all admissible U, something happens, okay? The control Lyapunov function statement is actually very hard because it says there exists a U for which my V dot will go downhill inside the set. That turns out to be very hard. There exists is a hard thing to write with these sums of squares, okay? If you could somehow turn it into a problem where you said for all U, something happens, okay? And the trick to doing that is to flip our argument inside out. And instead of saying that there exists a U that will keep me inside my region and go downhill, what you're going to say is I'm going to make a certificate which says that if I'm outside the region, for all U, there's no way I can get inside the region, okay? So and you try to make that region as small as possible. So it becomes an outer approximation of the region of attraction. Instead of a Lyapunov function, you think of it as a barrier certificate, which says that basically I can't get inside my region with this controller. And then you try to make that region as small as possible. So I did write that carefully. I can write that on the board if we decide that's important, that people are interested in that. But let me just give you the menu first, okay? And the reason, so that's a little bit, you know, I always thought about regions of attraction as a way to certify something. And if you're thinking about it as a certification, you want to be on the inside, right? You want to be an inner approximation of the region of attraction. You want it to be anything I've said I've certified, I will absolutely stabilize. Being an outer approximation isn't a certification, right? It could be that you've said something's inside this region, and it's actually not part of the region of attraction. But it's a better formulation for searching for controllers. And then you can put them together. You can use like the outer approximation to find the controller and then the inner approximation to certify it. That's a good way to do it. Okay. Both of them have the property that you can write them as sums of squares. As I increase the degree of the polynomial and the degree of the multipliers, you expect them to converge to the true region of attraction. One of them will converge from the inside to the real one. The other one will converge from the outside in.
How does finding a controller that won't cross into the region of attraction, how is that equivalent to finding a controller that won't leave the region of attraction?
So the statement is that for all possible U, V dot is still going, or sorry, my something equivalent to V dot is going downhill, okay? And then so that's the statement saying that for all V dot, or for all U, V dot's going downhill, and then you try to make it touch the boundaries as close as possible. And if you ever were to cross the boundary, then you would you would have violated the barrier certificate. So I can either do it with the whiteboard, or let me see if it's easier to pull this up. I'll do it on the whiteboard. I like that better. So for instance, let me do it in pictures first. Remember my cubic polynomial example that I really like, right? This. And we found a quadratic Lyapunov function that could prove stability. I'm going to learn something different now, which is I'm going to learn a v that's going. I'm going to learn something. So this was f of x equals negative x plus x cubed. This was v of x equals 1/2 x squared, was my original sort of Lyapunov thinking. For the outer approximation, I'm going to learn b of x, which I'd like to be, I would like it to still be that b dot of x is less than 0. But now I'm going to have it everywhere. Okay, and I want to say that b of 0 is greater than 0. And then I want to minimize b. Okay, so if you do something like this, then what you get is a function that, let's say I picked some small number at 0. In order to satisfy the dynamics, I have to have a function that looks kind of like this. Okay, so everywhere I look, this system, remember, when I'm here, it's going this way. When I'm here, it's going this way. When I'm here, this way, here, this way, right? So if I have this function like this, then it's always going downhill in that function. There's a 0, b dot could be 0 right here. But b dot is always, I guess I have to write less than or equal to 0. I should be careful of that. I'm going to try to find functions that look more like this red equation, okay? Say that they're going downhill everywhere. And then the argument says that since my fixed point is at 0, everywhere that's outside that started with like b less than 0 must be outside the region of attraction. So it's a barrier. So this is a proof that says that if I started less than 0, there's no way I could have gotten back to this fixed point. That's the basic idea of the outer approximation. I'll tell you how the control fits in a second, but first let me make sure that's true.
So it's basically like the opposite of the Lyapunov function. Instead of finding a function that always decreases to the fixed point, it's finding a function that always diverges from the fixed point outside of a region.
I don't want to call it the opposite. Like I was tempted to use those words too. Inside, it actually is acting like a Lyapunov function. Outside, it's still going downhill like a Lyapunov function. But whereas before we were saying, you only have to match the Lyapunov conditions inside, here we're going to do it everywhere. And know that because of the Lyapunov-like conditions are met everywhere, if I'm ever below 0, I can never go back up. So that's why it's an outer approximation, right? So the true region of attraction is this set here. It's going to come up with this outer approximation, which is the b of x less than 0, less than or equal to 0, implies outside the ROA. I mean, it's as important to me that you just sort of, yeah, appreciate the style of arguments that people are using, but this seems like in the case of just proving a region of attraction, you might not use this because it's going to potentially lie to you. Both of them have the property that they will converge to the true region of attraction if the degree goes high enough and the monomials and the degree of your multipliers goes high enough. This one will be outside always. This one, the ones we've done so far will be inside always. The thing that's magical about this is that we can do control design in a convex way. So if I were to put in control design, you see there's no multipliers there that multiply lambda. There's no lambda of x times v of x or anything hiding here. You have to do one more trick, which I wasn't going to mention, but I see that I've walked myself into, of the partial v partial x times k of x you can handle, but you use a for all x kind of approach. You use it as a slack variable for this. Okay, so but I mean, so please ask questions if you have it. I know I didn't give enough to fully appreciate it, but. Does that make sense? I mean, does the notion of a barrier kind of make sense? We also use them for going around obstacles. You can say like, I will never run into this obstacle because I've proven that there's some barrier. I'm proven that my initial conditions are less than 0 and the obstacle is always greater than 0 and the barrier dot is going downhill. So I'll never go in there. It's another way to turn a derivative property into a, where can you get to property.
What did you mean when you wrote min b? Is that minimize over b, or are you trying to minimize like the magnitude of b somewhere?
Nice. You come up with some surrogate of minimizing the function b. So you're going to like basically compute the integral over the function and push down on it.
So in other words, you're trying to push b as close to the true region of attraction as you can. Like you're trying to minimize the gap, basically.
Yeah. To make, I mean, these things will make your head spin. To actually make it numerically good, what we do is we put a different function on top of b and push down on it, but keep it positive so that you don't want to try to push things to negative infinity. So we put this other thing that stops at 0 and shove down on that. Okay, and that turns out to be the numerically good way to do it. And you can also use simpler functions to push down. So the outer approximations go farther for control design. You will see people talking these days about contraction metrics too. They're similar ideas. Instead of a Lyapunov argument, you can have an argument that's kind of a differential Lyapunov argument. JeanJacques Slotin in mechanical engineering was popularized these approaches, and there are things that look a lot like our control Lyapunov functions that do control contraction metrics. And there's been a couple of good papers in the last couple of years, including from JeanJacques. But they're all in the same kind of space. It's more about what type of stability you want to prove. The last one that I'll mention, which I think actually doesn't get enough play, would be a great final project actually, if anybody wants. Any of these would, but so you can take the Hamilton-Jacobi equation, turn the equality into an inequality, and think of that as a sums of squares optimization. And then that would be a lower bound on the cost to go. And then you push up on the lower bound, basically. And that would be another way to do control design. And it does work. you tend to, in our experience, you tend to get to pretty high degrees pretty fast. But I actually think it's, I think nobody has really coded it up carefully enough to see how far it goes. But I think it does very well in the hierarchy of these kind of control problems. So where does sums of squares land for you guys? Is this a cool new trick? I'll never use it again. Is it, I should change my research direction to do only this? Where are you guys landing?
Hopefully somewhere in the middle of this.
That's fair. That's kind of expected, I guess. I do think the tools are, so when my group started working on this, we had the luxury of having Pablo upstairs, and it took years, I would say, so there's a difference between when people like Pablo write papers about sums of squares and come up with examples, and they write the perfect formulation, and they hand this beautiful thing to the solver, and the solver, just cruises through it. There's something very different that happens when you say, here's a bag of equations that I got from my robot dynamics engine. I'd like to prove something about this. The thing that happens is you get like a lot of terms that would be zero that Pablo would have just crossed out. Like, obviously I don't need to include that one, right? But like a lot of the coefficients of the polynomials that I include almost by accident because I don't know how to take them out in a generic way for all robots. He just would have scratched them off, and he can term match and all these amazing things. Like, I know that if v dot and lambda times v need to cancel each other, then lambda needs to be some degree that's at least as big as this, and you can kind of term match and do all these extra tricks. And if you don't do those tricks, then you're left with a lot of coefficients that need to be set to 0, and those mean in a semi-definite program that you're on the boundary of the SDP cone. And that means numerical woes. so it took sort of years of bottling this up and making it a robust enough thing that you can say, here, give me your equations, give me your robot, stabilize it, and have sums of squares kick out. But it's gotten to that point, I think. And so I lost some of it when we converted Drake from MATLAB to C++. I haven't put all of them back in, but there is a region of attraction code in C++, which is also then Python. If you guys hammer on it, if you hit a system that it doesn't work for, there's probably a version of it that would make that work. And I would like to build that back up into being a really solid thing. So cool. Anything else?
I have a question.
Yeah.
So this alternation approach, in order to find both a controller, I think a controller and a Lyapunov function at the same time, could it be used like in the, we had a way to, just before that you talked about a way to use the S procedure which allows to find lambda and rho. So if you have so could you use this alternate approach to find lambda, rho, and v at the same time?
I'm so happy you asked that. You're thinking all the right things, but unfortunately, no. so the problem is v and v dot both, like if you have the coefficients of v you're searching for, they're also in v dot. So with the special case of rho, that affected the v term, but not the v dot term. But as soon as you change to the more general version of searching v, those coefficients enter both of those equations, and the trick of the equality constraints doesn't get around it for you. But that's exactly, that's exactly the right question to ask and to think it through. Yeah, unfortunately, that one doesn't pan out. But things like that do pan out.
for this notion of like warm starting basically V or K in the alternations approach with some sort of like, yeah, that feels like one, is that a thing that people will do in intelligent ways? And then two, we had at some point been touching on like, oh, a benefit over sum of squares versus the sampling based approach is that you get this certificate. Is this a practical approach that people are using to sort of certify, you know, let's say I'm like totally an RL person. I gave you a controller or something and I'm like, make it a little better so it's safe. Is that like a thing that people do, or is that, or an approach?
Such a good, like I couldn't, you know, so it happens that I'm attending a workshop sort of this week on robot safety and learning. And my gosh, the robot learning people are talking about safety sets and, you know, barrier functions and all these things, right? So, I mean, I sort of feel like there's a bunch of people in reinforcement learning that know safety is important. And then there's a bunch of people that control that know bigger problem formulations are important. And, you know, that handling cameras and open worlds and stuff are important. And they're kind of both slowly working together, right? And they're kind of pointing at each other, at least, you know, using each other's words and saying where things don't match. There's probably some extra ideas like off to the side that we need to really solve the problem, but yes, I think people are putting these tools together. I do think they work for small problems. They don't work for perception, for instance, yet. You would need to get from your perception system down into some other smaller dynamics to verify it. There are people that are doing neural Lyapunov functions now. I'm going to write a small section in the notes about that too, and we've got some work in there in that space too. I think if you really want to say something about global stability with a neural network, then you can do that, but only for modest size neural networks. I would say small neural networks. So they're not into the regime where the neural networks are really, you know, doing their magic of overparameterization and the like. So you will see papers about, you know, verifying neural network controllers and stuff, but they are probably not the neural networks that are doing perception yet. But that's a dream, you know, to kind of bring those all together. It's not only safety, it's also, I would say, guaranteeing performance, right? I mean, you can have a statement with a Lyapunov type function that gives you a guarantee on total cost. So it's not even just about, am I going to run into something? You can also, or, you know, can I guarantee I'll converge? You can also put, make statements about just that I will achieve a certain score, for instance. These are all related machinery. Do you have any specific robots systems that you're thinking about maybe applying it to without changing your whole research direction?
I guess a question I have is, can we use Lyapunov kind reasoning to make some kind of assertions about the stability of cycles instead of specific states or specific, yeah. So I'm thinking of having something like a walking robot. Can we say something about a controller that, where is the region of attraction for the walking cycle, for example?
Yeah, you're making this easy for me. That's coming up for sure. That's something we've definitely done, right? So the picture is you have some limit cycle, and that also has a region of attraction. We have to define the notion of orbital stability of this, because you want limit cycle stability is slightly different than trajectory stability, but we'll talk through all those. Yes, and yes, you can do it. You end up solving for a periodic Lyapunov condition, a Lyapunov function that's periodic that goes along there, and you try to show that it converges to the cycle.
Awesome. Thank you.
Yeah, no, I love the question.